he gave the two Lyft guys 30-minute slots and the Uber guy 45 minutes, so you should be happy. And so that's an optimization problem he solved. The speaker of the last speaker session is Sid, who's going to tell us about dispatch.
All right. Thank you very much for the invitation to speak in this session. This is somewhat daunting given the list of other speakers, but I hope I have something interesting to say. So the one thing is the talk is very different from the previous talks. In particular, I'll actually go back much more into the theory of what ride-sharing systems are, how I think the theory of ride-sharing systems works, and what are sort of the interesting theoretical questions. So kind of tying it back in more with what's the aim of the Simons workshops in general. And this is, so I'll present two pieces of work which were done with a set of amazing collaborators. So Daniel Freund sitting somewhere in the back of the room. He's currently, or is he? Oh no, he's standing at the back of the room. Okay, he's currently at Cornell, but he's soon heading to MIT by way of Lyft. Theodoros Likoris, we saw his picture yesterday if you attended Eva's talk. He's supposed to be here, but he's exploring the life of being a traveling researcher. I think he was last spotted in Chicago or something like that. So that's sort of work which I briefly talked about for those of you who attended the bootcamp workshop, but I'll kind of summarize it again because there's some people here who I'd love to tell this work, who I'd love to describe this work to. But the main focus of this talk is going to be on some work we've been doing more recently, and this is joint work with Peng Yu Qian and Yash Kanoria, who are both in the Columbia Business School. So without further ado, what's the dispatch problem? So this is the kind of highly stylized problem that I'm going to focus on for the entirety of this talk. So what the problem is as follows. You show up in 4th Street Station. You want to get a lift. You sort of request a ride. The platform knows that there are 5 of these cars waiting around, and it needs to decide which car to match to you. They're all sort of the same distance away. It's not going to affect you in terms of time. But perhaps it affects the system in some larger sense over time. And the question we want to ask is, how should we make this decision, and how does this affect the missed requests in the future? Okay. And given my background, I'm going to try and model this as some sort of stochastic decision-making problem. So in particular, here's the model that I'll be considering. This is the same thing I presented in the bootcamp talk. So essentially, I'm thinking of the system as being comprised of a fixed number of stations. So think of these as localities in the network. So here we have n stations, these big circles, and there are k cars, or I'll call them units, which are sort of scattered across these stations. And at any time, the state of the system is where these cars are located. So for each station, how many cars are located at that station? The identity of the car doesn't matter. And I'm going to assume that there's a stream of passengers who are arriving at station I, wanting to go to station J, and they're arriving according to a Poisson process with rate phi j. Okay, so what happens if this passenger shows up? Well, the passenger requests a ride if the price is reasonable. They get matched to an idle unit. They get into the car starts driving towards the destination. This usually takes some travel time. We're going to assume it's independent. And actually, for this talk, to keep things really simple, we'll assume all the trip times are 0. Some of the results carry over with this. Some require this. And I'll mention that as I go along. OK, so what happens if someone comes and sees that a unit is not available? So what if you come and see there are no cars where in your neighborhood? Well, the assumption I'm going to make is that the customer is myopic. They have some other option. Perhaps they could use this thing called Uber. And so what they'll do is they'll just leave the system. Right? And what I want to do is I want to minimize the long-term average rate at which I miss these requests. So someone showed up at Lyft. They really wanted to take a lift. We didn't have a car to offer. And throughout this talk, again, to keep things simple, I'm going to assume that the prices are fixed. So I'm only focusing on the dispatch problem. Okay, so what's the dispatch problem? Well, I didn't really need to lose this guy. The reason I'm thinking that this person's not going to take the lift is because there's no car available in the immediate neighborhood. But maybe, as Garrett was mentioning, maybe the person's a little more patient. And maybe I could offer him a car from a neighboring neighborhood. So somewhere close by, such that the time it takes for that car to show up is not too high. And the other sort of big assumption I'll make throughout this talk is that this is essentially for free. So what I mean by that is there are a set of localities which are close enough such that if you send a car from there, for the passenger, it's as if you send it from the same neighborhood. This is clearly not true. Some things, again, extend without this assumption. Some things don't. But it's sort of a very interesting simplification one can make, which gives very interesting insights into the problem. Okay, so that's the setting. And I'm guessing at this point, most of you are sort of looking at this and thinking, OK, I've seen this problem before in one form or the other. Or you're thinking, OK, clearly this model is inadequate. It's like not capturing many things. So, so before I go there, let me kind of set up this model in a slightly different way. So this is what I'm calling the bipartite matching with externalities problem. So the idea is, here again, we have 3 stations. And what I've shown here is which station can call vehicles from which other station. So every station can use vehicles which are located in that station itself. But 2 can kind of summon vehicles from 3. 3 perhaps can't summon from 2. Maybe there's a high-speed or a one-way road from 3 to 2, and so you can't go the other way. And similarly, 1 can summon from 2, but not vice versa. So that's what that graph represents. And what I'm doing is I'm kind of converting it into a bipartite graph, where I'm saying that I have the same stations drawn on both sides now. On one side, you have supply. So these are the cars which are waiting at each of these stations. On the other side, you have passengers who are showing up to make ride requests. And the graph is encoding where can you pull supply from for free. Is that clear? And just a bit of notation. So the lambdas are, suppose we never lost a ride. The lambda essentially represents the total amount of passengers who are showing up at station 3. So I'm just adding up over everyone who wants to show up at a station. And similarly, mu is the total number of passengers who show up at the station looking for a ride. So these are sort of people showing up at the destination. These are people showing up at the source. So the problem as is looks exactly like bipartite matching, with this interesting sort of twist that when you serve someone and that person goes to the destination, then you're sort of changing the supply at the destination. So that's the notion of the externality that I have in the title. And if you think a little about it, it's clear that if I just ignored all this like Poisson and all the stochastic business, I have to have that for every station, the total supply available for it is more than the demand which shows up. Like that's a minimum requirement in order to be able to serve everyone. That has to be true. Otherwise, sort of basic Hall's condition would say that you can't do anything. And in some sense, what this talk is about is, OK, how do we actually come up with policies which handle the stochastic fluctuations? So that's the entire model. That's what I'm going to sort of focus on for the rest of the talk. Yes?
You're, for the moment, ignoring the transit time.
I'm going to ignore transit times throughout. Yeah. So it's OK. I mean, many of you should have a lot of questions at this point. You shouldn't be satisfied. There are many things missing in the model. And so a little intermezzo. Why this model? Why should I even care about this really simple problem? So this is a picture which I actually first saw in this beautiful book by Jason Hartline on mechanism design. It's actually a sketch by Picasso looking at bulls. And what Picasso is doing is Picasso sort of starting off with a bull and then kind of deconstructing the bull in different forms. Right? So kind of giving lesser and lesser information, reducing extraneous details, etc. And the way I sort of think of this is, in some sense, all of the sketches are beautiful. Like it's not that any one sketch is the true sketch of the bull. There is something interesting going on in each of these sketches. And to me, at least, that's actually true for any model for a real system. All models are inaccurate. I mean, you can never capture a model in complete detail. And what's really more important for me is what's the question that drives the model? And is your sort of model correctly matching up with what you want to answer? So what do I want to answer? These are sort of some of the things that I'm hoping to get to in this talk. So what is the correct structure of dispatch policies? If you're running this Lyft or Uber's dispatch system, what should you be worried about when you sort of design these policies? What's the value of actually doing real-time dispatch? Or is it OK to not do it in real time? Can you have something pre-programmed versus real time? What's the role of information in the system? How does it matter? Does it matter how accurate it is? Sort of, should you hire one more data scientist, or should you be hiring queuing theorists? And sort of a very meta-level question. I'm kind of ignoring pricing throughout, but is that even fair? And this is actually a really deep question, which I think all ride-sharing firms kind of struggle with to some extent. I mean, there's a sense in which pricing and dispatch are coupled together, and that just makes life really difficult. So is it fine to ignore, like decouple the two, or are there sort of fundamental couplings between the two? So that's this kind of question I want to get to. And the way I think of it, we are really in sort of this kind of world. So this, for me, is sort of the economic models or the sort of CS theory, the K-server models, which are very, very sparsely specified. There's 1 or 2 parameters to define the whole thing. This is kind of closer to like these simulation models. If you all saw Samita's talk yesterday, these are like really complicated, beautiful visualization, things moving around. But it's unclear if you can answer questions of this sort in a model like that. For me, that over there is really the kind of thing Alex was talking about, like real systems, slightly abstracted, and then trying to do something interesting with it. Whereas the world I live in, this sort of world of stochastic control and models with like stochastic assumption, is kind of over here. And there are many more gradations, but that's the picture. And that one's kind of beautiful. So yeah, let's focus on that. Why else would I want to? Why else do I think this talk is interesting? In some sense, if you don't even believe anything I say in terms of ride sharing, and many people don't, and that's fine, I think it's sort of nice that there are these really deep connections between these really fundamental problems in ride sharing and very deep questions in algorithms and control. So these are sort of 2 recent theoretical advances which I found were truly amazing. So one was this whole line of work on the optimal control of input queued switches by Shrikant, Sivateja Maguluri, Vena, who's somewhere here. And secondly, there's this sort of long-standing conjecture about thinking about the online K-server problem. And there's been some amazing advances made in this. Actually, in both these problems, they were both open for something like 20 to 30 years. And in both these problems, we've had recent advances, which kind of took everyone by surprise. Unfortunately, the problem I was looking at was not considered open. Somehow people hadn't thought about it. But what I'll try to convince you in the remaining time that I have is we think it is in some sense reached a fairly satisfying closure. So that's the intermezzo. So back to like, so what's the main question that we're looking at, and what do we do in this problem? Okay, so this is again the main question. So we had these n stations, k units, Poisson arrivals. There's some assumptions to just make sure this problem is not trivial. You can't just pull a car from anywhere that you feel like. There's some tension in the graph, and you need things to be reducible. You can take care of stuff like that, but just let's assume we have that. And we're given this bipartite compatibility graph, which tells us where can we pull supply from for free. And what we want to understand is, how do we come up with a dispatch rule? So how do we come up with a rule which maps the current state to a rule to deciding who should serve whom, which maximizes the rate at which we can actually serve the people coming in the steady state induced by this dispatch rule? So it's a little complicated because the dispatch rule is looking at the state to do something, and then we are letting it run, and eventually this is a finite state Markov chain, so it's going to reach a stationary distribution. And in that stationary distribution, I want to understand how well we are performing. Is that clear? Why can this be tricky? Well, one obvious thing is that the state space is exponential, and so the policy space is also exponential. We are allowing the policies to look at the state at any time and decide what to do. So that's sort of the typical the curse of dimensionality. A slightly more hidden and a more subtle thing in this problem is that this problem is non-convex even in very, very simple settings. So even if you have state-independent dispatch rules and I think 1 vehicle and 2 stations, that's like the least we got it down to. Beyond that, it's trivial. But even in a case like that, this problem is non-convex. So if you try doing any sort of standard thing by just running gradient descent, maybe it'll work, but there are no guarantees that it should. Yeah.
Maybe I missed it. What is chi-ij?
Yes, I'm sort of skipping things a bit. So chi-ij is it's an indicator that if a guy shows up at I, under this dispatch rule Q, he is actually being served in state X. So I'm sort of packing all of that into. Should take a slightly impressionistic view of it. This is the steady state rate at which people are being served.
Using energy use and greenhouse gas emissions.
That I guess is not a question. Okay, so that's kind of what's tricky about this problem, and perhaps that's the sense in which this is why it wasn't even considered an open problem. It didn't really seem like there was anything tractable that you could do in this setting, and so it was a great delight for us when we figured out you could do something tractable. So the first work that we did, this is work with Daniel and Theodoros, where we basically showed that there's a way of getting a state-independent dispatch policy. So I'm not even going to look at who is there, where the vehicles are located. And this comes out of a flow relaxation, so it's actually a pretty easy to compute policy, but you can give very, very good guarantees for it. So in particular, you can show that the policy is within a 1 plus n over k factor. I'm sort of like making everything positive or greater than 1. So it's within 1 plus n over k if you have instantaneous trips. This is actually an exact bound. Like there's no hidden constants anywhere. With travel times, the bound gets a little messier. You can, again, compute it exactly, but what you can show is in the worst case, it's 1 plus order 1 over square root k. So yeah.
Sorry, could you just remind us what n and k are?
Sorry, so n was the number of stations, k is the number of vehicles. So I'm thinking of a world which is somewhat dense. There are more vehicles than stations.
What's flow relaxation?
I'll not come to that, but this is what I was talking about in my the bootcamp. So essentially, we'll ignore some of the fluctuations and construct an optimization problem, which turns out to give these guarantees. It's not. I'll briefly mention it, but yeah. So I'll go over this quickly because this was work I talked about before. But so the interesting thing about this work is it's actually extremely general. So even though I'm sort of talking about the dispatch problem, it actually works if you want to think about pricing, if you want to think about actually taking driverless vehicles and rebalancing them. It works for revenue. It works for welfare. It works if you want to do fancier stuff than that. It's just a very, very nice general technique for solving any of these close control problems. And it also gives what's called large supply or large market optimality. So these are kind of much more specialized tools in probability which people have developed for studying these problems. And in some sense, we are just circumventing all these specialized tools and kind of showing all of this in an elementary way. So it was really pleasing to get these results. The problem was that we are kind of stuck at this 1 over k or 1 over square root k rates. And we were wondering, OK, can you do better? And what we managed to show more recently, and this is work which we just sort of finished writing, and this is work with Yash Kanori and Pangyu Qian, is that actually you can do better if you use state-dependent dispatch policies. And in particular, we can give you a family of state-dependent dispatch policies, which all get you exponential decay in this, the rate of which, the suboptimality. And you can't exactly nail the pre-constants, but if you are just interested in the optimal exponent, you can find that using a convex program. And so that's going to be the main focus of the talk today. Any questions about the results or just what they mean? OK, I'm going to sort of briefly go over the previous argument because that comes in to a small extent in the new work. So the way we constructed this state-independent policies was by this flow relaxation. And this is something we call the elevated flow relaxation. And the basic idea is that you kind of relax this. So we have this really complicated objective with all sorts of like probabilities, blah, blah, blah. But you kind of relax this into a flow program. So you just optimize over the fraction of I to j requests that you accept in steady state. We don't know what this is, but like how to achieve this. But let's just optimize over that. And we only encode sort of essential conservation laws, things which can be encoded as flow. So things like flow balance and Little's law. Actually, these are the only two that we encode. This doesn't make sense, not too important. You can go back and see the bootcamp video. But sort of what we then do is we take this program and we show that it is tight if the number of vehicles goes to infinity. So if you keep everything constant and set the number of vehicles to infinity, any policy in this flow or any of these flow relaxation, any point in this polytope can be achieved by some policy in this space. And we know what the policy is. And then we do this sort of interesting thing where we take the infinite policy and kind of pull it back to a finite system. And the way we did that, and I'm being a little indulgent here, but I kind of really like this proof. So essentially, we construct this sort of sequence of product form chains and somehow bound these normalization constants. So this is kind of work stemming from like the seminal work of Frank Kelly long back in the 80s. And it's unfortunate he's not here, but it's kind of an interesting use of the techniques that he had developed back then. And sort of combining these, we get this result that the objective in the k unit system, if we use the infinite unit policies, is within this k over k plus n of the objective of the optimal solution in the k unit system, although we have no idea what the solution is. It's somewhat impressionistic. We can blame it on Alex for less time, but I'm going to actually move on to the next part. The main takeaways, again, being that we have this sort of new technique of getting these state-independent controls. And the two big problems being that the way we actually find these controls that we really need to know the demand rate and the price elasticities. And these guarantees are actually tight. We cannot do better than what we've shown over here. We know sort of counterexamples. So what I want to talk about is how do we go beyond this. Okay, so again, to try to even understand how to go beyond this, I need to go back to this original problem. So I have this bipartite graph. I'm trying to decide who gets matched to whom, and I know that all these servers kind of like they keep moving based on how we match them up. So we have these flows of servers and of demand. And a slightly different way of looking at exactly the same system is actually to look at the fraction of servers who are located at each location. And now what you're doing is once you normalize this, you're actually sort of embedding this entire space in the simplex. So you're taking the state space and then sort of putting it as you're plotting a point in this k-dimensional simplex, the n-dimensional simplex. And in some sense, what the system is doing, or what the system plus the control is doing, is it's actually doing a random walk in the simplex. And the problem happens as long as you're in the interior of the simplex, you're fine. There's always some vehicle available for you to match up. The problem happens when you're sort of hitting the boundaries. So at the point at which you hit the boundaries, then all bets are off. Maybe someone comes in and asks you exactly for the vehicle which you don't have. And so what we really want to do is, okay, we have this random walk going around in the simplex. Can we sort of change the controls to make sure it stays in the interior as long as possible? And the sort of formal way of thinking about this is, instead of, it's kind of hopeless to analyze the process exactly, or at least I don't know how to do it, but what we do is we kind of scale the number of vehicles to infinity, and then we look at what's called the large deviation exponent. So we are trying to target an exponential decay in the fraction of dropped requests. What I'm going to do is I'll reparameterize the system to just look at exactly this quantity. What is the coefficient of that fraction? Is it greater than 0? Am I even getting an exponential decay or not? So for those of you who've seen large deviation, this is exactly the rate function of this with respect to k. But if you've not seen this kind of treatment, just think of it as, we know we are trying to get an exponential decay, so let's sort of zoom into the exponent and try to see how good it is. Right? Now, what I said earlier was that the policies that we had for state-independent control were tight. It actually turns out that they are tight in a much sort of wider set of policies. And the crucial thing that lets us get out of these sort of non-exponential decay is this assumption. So what is this assumption? So this is something called complete resource pooling and queuing. But essentially, if you've ever seen Hall's condition, this is exactly Hall's condition, except with a strict inequality instead of a greater than equal to. And you could ask, okay, is this really necessary? Do we really need Hall's condition? So I'm sort of looking at Hall's condition in this graph with a strict inequality. And well, it's clear that the greater than equal to is essential, because if that's not true, just by Hall's theorem, you must be dropping demand. But what it turns out is that the strict inequality is actually essential. So in particular, if this held with equality, we have a proposition which shows that you cannot get exponential decay. So the only hope of getting any sort of exponential decay is that you actually have the strict Hall's inequality. Now, how much time do we have? Can we call it 5 minutes?
3 minutes.
Okay. Can we negotiate? Learning from Alex. Okay, so the main result that I'm sort of trying to I'll try to build up to is the fact that as long as you have this condition, you can actually always get exponential decay, and in fact, you can get the optimal exponential decay under this sort of stricter Hall's condition. And one way of thinking about what the policy is to kind of think of a kind of straw man policy. So this is the most natural greedy policy that you think of if you were designing the system. It's in queuing, this is called MaxWeight. And the idea is whenever, let's say someone shows up at 1, you look at all the compatible queues, and you say, okay, this guy has so many cars, this guy has so many cars, well, he seems to have more cars, let me pull a car from there. It's a very, very natural, like local greedy policy, which has this amazing property that in many queuing networks, in particular any open queuing network, where like things come in and go out, it's actually known to be optimal in sort of very strong senses. And this was the result that Srikant and Shivateja proved after. But there's a long line of work by Sean and others before that. And so a natural question is, okay, how does MaxWeight do in this case? And it's actually not difficult to see it's suboptimal. Now, if you just think of the car demand coming in at 1, a car at 2 can serve both 1 and 2. A car at 1 can only serve 1. So it's sort of strictly dominated. So you'd rather use up this resource before using up this. So you can kind of exchange the two. Does that make sense? So there's no reason to actually use 2, but MaxWeight will say, well, there are more cars there, you should use it. So this cannot be optimal. And the thought is, OK, can you somehow patch this together and try to get something optimal? And so here's sort of a natural extension of MaxWeight, which is, OK, greedy doesn't work. What about scaled greedy? So what if I sort of have a weight for each of these queues and then do greedy with this sort of linear scaling? And this is what we call the scaled MaxWeight policy. And the idea is exactly the same, but except that instead of pulling from the maximum queue, I pull from the maximum queue divided by this weight. And now you can see that if the weight for 1 goes to 0, I'll never actually pull from this queue. You need, or rather, I'll always pull from this queue if the weight goes to 0, no matter how many cars are there. So it's a much wider class of policies, and kind of the question is, how does this perform? And the main result that we have is that this class of policies is actually optimal. So there exists a way of choosing these weights. In particularly, the way to choose the weights is from this horrible-looking optimization problem. But if you choose the weights according to this policy is optimal for the rate function. Now, what is this thing? Don't try to parse it. But the main thing is everything is positive. Remember, we want it to be positive to get an exponential decay. So everything here is positive. The only way this is positive is the numerator is bigger than the denominator. And the numerator is sort of the total flow coming into the cut, whereas the denominator is the total flow going out of a cut. So essentially what we are saying is the rate function, or the ability to get an exponential decay, is kind of connected to a min-cut problem in this graph, but it's sort of very complicated min-cut problem with all these bizarre logs. And this is tight. So what you can actually show is a converse result where you can show that any policy, any state-dependent policy, cannot achieve better than a certain rate. So in a very, very strong sense, there exists a weight which is tight for this problem. Or there exists a weighted max weight policy which is tight.
So sorry, just how do you choose the weights? You weight it based on?
We solved this problem.
First, I see.
Yeah, but I'll give you a little bit of intuition. So now So here's some intuition how to choose the weights. I mean, this is really abstract, so sort of I want to now convince you it's actually useful. It turns out that the way to choose the weights really depends on the information structure. It depends on how much information you have about the entire system in order to actually solve that optimization problem. So if you had no information, what you would do is you could choose all the weights to be equal, in which case you get exactly the max weight policy. And one sort of offshoot of our result is that MaxWeight does give you exponential decay, except that the rate function is not optimal. So the coefficient is not optimal, but it's off by at most a factor of n. On the other hand, if you knew everything perfectly and you were really brave to try and solve this problem, you could find something which had the optimal decay for this problem. But in some sense, and this is what I think is much more interesting, this is kind of what we are trying to think about now. What if you had partial information? So the problem really captures this notion that in ride-sharing, there are these sort of cuts which are very critical. So there are cuts where there's more drain from one end versus the other, and you need to somehow protect those cuts. And this, if you could parse through what we wrote, it essentially captures exactly this notion. How do we protect all cuts simultaneously in the network? There's another really interesting thing which we kind of observe right now, which is that there's a sense in which the theorem actually implies that there's a separation of pricing and dispatch. So what we're saying is once you fix the pricing, you can get an exponential decay you can basically serve everyone with with exponential 1 minus e to the minus something probability. So in some sense, you could have done the pricing just based on the flow problems and then done dispatch in real time. And at least in theory, that should be enough. Unclear if this holds in practice, but it's at least it's interesting that we can say something of that sort. Okay, so I'm going to skip the proof. So it's technically messy. They're fancy-looking Lyapunov functions. So you have to use a Lyapunov function on the simplex using some interesting tools. But sort of just to leave you with what we did and what I think is interesting. So this has been kind of a long line of work thinking about these problems, and we feel now we have a really good understanding of what it means to design good policies for these problems. So what it means to design good state-independent policies using flow relaxations, and what it means to design good real-time policies using these sort of scaled max weight ideas. But there's sort of a bunch. There's a huge number of things which we don't know. So we don't, everything, the second half of the talk, using scaled MaxWeight, we didn't actually use travel times. We know if travel times show up, things change. At least in the extreme case, you cannot do better than 1 over square root k, but what is the scaling if you have travel times thrown in? Now, the proof of the last part was really, really heavy machinery. We're using these like Lyapunov functions and large deviations. I strongly feel that there should be an elementary proof of this fact that you can get exponential decay, but okay, elementary in quotes. And this is something we've been thinking a bit about. We have some ideas, but it doesn't seem an easy thing to solve. How do we adapt the information? How do we adapt policies to information structures? What's sort of the banded version of thinking about these problems? Something which I know David's been thinking a lot about. How do you sort of patch together dispatch when you do ride pooling? We are only assuming a single ride, but what happens if you can do multiple rides? So there are a lot of sort of interesting open questions. I'm hoping I've convinced you there's interesting theory to do. So even if you're not working at Lyft and Uber and you can't talk about what you do, there's still sort of interesting problems that you can just kind of sit back and think about. And yeah, thank you very much.
Okay, so like it's sort of about sort of scheduling where you get feedback from the jobs that you serve. So one thing to say is that, well, MaxWeight isn't maximally stable when you have networks, so there's when there's feedback between the nodes.
And there is no feedback.
MaxWeight is if you divide by the traffic intensity of each node. So I kind of interpret what you're doing in that
It's
way.
close, except, yeah, I mean, I think.
It's a different model.
No.
I can believe that works. Also, Vice did some stuff on queuing systems where you can inject customers and then pull them out, and it's sort of meant to be like a silicon manufacturing example. You can do back pressure for that, and then instead of sort of deducting off some terms, you add them. If you see what I mean, so I could imagine that could apply in this type of model. And then
We should definitely.
models that work for kind of multi-hop networks or networks with feedback, it's weighted max weight, where you divide by the traffic intensity, back pressure in the way for applying it in that kind of Vice model.
Yeah, so, okay. Am I claiming this is unbelievably surprising? No.
No, I mean,
But I do think it's, okay, it was fairly non-trivial to show this works. And partly what's really irritating in this whole system is because it's closed, you kind of don't have directions in which to go out. So there's no state space collapse in a certain sense.
It's kind of a maximum matching thing if you looked at like kind of the Stolio virtual queuing stuff.
So I'm assuming you can't wait too much. Yeah, we should take this offline.
Take this offline. Thank you.
Thank you.